Let's take a look at the parameters. And here I'm not going to go through each one in a lot of detail, but we have things like DL. This is where we use the resolution. So resolution times y max minus y min. So basically the length in y times the resolution will give us the step, the grid size in y. And then we use that to calculate the number of cells in x, y, and z correspondingly. And DL will be our grid spacing in all three dimensions. Once we actually have an integer number of cells, then we need to recalculate the dx, the dy, and the dz, because we rounded during this calculation of the cells, and so we want to get the real value of the grid spacing. Here's our dt, which, as I said, we use the CFL condition, we use the grid spacing, we use the speed of light, and we use this diameter fraction here. You don't need this dt calculation necessarily. VSim will calculate that for you automatically, but we have it here so we can see what it is. The next parameters that I'm going to go over are all to do with the generation of the current density function to drive the electromagnetic field we're looking for. We'll start off with this frequency low. This is 0.8 times the frequency, so this will help define the lower bound on the frequency band we're going to drive. Frequency high is 1.2 times the frequency we think it is, so that's about 1.8 gigahertz. And then frequency mid is the frequency that we suspect is the fundamental frequency, 1.497 gigahertz. These next few parameters are to do with the actual function. So I'm going to show you the mathematical form of the function that we tend to drive. We can see here the driving signal is for the current density, J, and what we're doing is driving some amplitude times two sine functions, and those functions have the frequency high and the frequency low for their frequencies. And then we normalize them, and we have this Gaussian envelope in time that is a function of t, but also we can see then this df is 1 over sigma of that Gaussian. And that df is defined as the difference between the high and the low frequencies. In this case, that was roughly 600 megahertz, and then divided by 4, so roughly 15 megahertz. And then that's all multiplied by this Heaviside function that turns the signal off after t off amount of time. Let's look at what this equation looks like. In time, we can see that this is a Gaussian and this is a log plot, so it's an oscillating signal with a Gaussian envelope that has a peak at a certain time and it turns off at twice that time. What we expect to see our signal to look like in the actual cavity is this ring up, and then though the drive goes down, we expect the cavity itself to continue ringing at a comparable amplitude to this maximum amplitude. Now let's look at the FFT of this signal, and we can see this is exactly what we want. This is a band of frequencies from F low to F high that we're driving. Okay, now let's go back and look at the parameters. So this delta is that frequency I was talking about, high minus low over 4. The num sigma is how many sigmas are required to get to the point where our amplitude has decreased by the suppression factor. So the suppression factor is 1 times 10 to the negative 8. That means our maximum signal will be 1 times 10 to the 8th bigger than where we want to essentially turn the signal off. And you can see this is 6 sigmas. This sigma t then is the time for 1 sigma in our function. So then our excite time is going to be the num sigma times the sigma t, or how long in time 6 sigma widths of our Gaussian is, times 2, because we have a rise and then a fall. So this is how long we want to excite for. We need to know how many steps that is in our simulation, so we divide that by dt, and we add 1, just to make sure that we're rounding up. And then the rest of these will have to do with the analysis afterwards, so I'll talk about those later.